In this lecture, we will continue our previous discussion on deriving a relation for effective diffusivity of a passive scalar which is being advected and is diffusing in a steady flow between these two parallel plates. And because of Taylor-Aris dispersion, it appears that along the direction of the flow, the solute or the passive scalar has higher diffusivity, and that is what we call as the effective diffusivity. Now, till now, what we have done is that we are looking at time scales which are larger than the radial diffusion time scales, and for such time scales we expect that the solution for concentration can be split into the depth average concentration, which is not a function of the y coordinate, okay, and plus this small perturbation which is C prime, and it is significantly smaller than this mean concentration, and that's because we would expect that because diffusion is really fast in the radial direction, therefore there would be really small gradients in the vertical direction in the concentration. Now, based on this assumption, we derived the governing equation for the mean concentration in the last lecture, and we got an equation like this, where we had these four terms, and out of these four terms in this equation, the three terms were in terms of the depth averaged concentration C bar, but we were unable to compute this term directly. So after some analysis, we were able to obtain an equation for C prime, and we obtained this solution for C prime. Now in this lecture, we can exactly compute this term over here. So what this term is that it's the U times del C prime by del X, and we are taking the depth average. So this is actually 1 over 2h integral of from minus h to h times the velocity, which is 3 by 2 times u times 1 minus y squared over h squared, okay, times del C prime by del X. So from this equation we see that del C prime by del X is u, which is the mean velocity, over 8 times the diffusivity. So if we take the derivative with respect to x, we will now get del squared C bar by del X squared times 2y squared minus y4 over h squared minus 7 over 15 h squared, and we need to integrate this whole term over y. If we do so, this is what we're going to get. So first simplification is that we have an even function over here, so rather than integrating from minus h to h, we can just take 2 times the integral from 0 to h, and these two cancel out. So eventually, if we try to bring these constant terms outside this integral, this is what we are going to get: 3 times u squared, okay, over 16 from this 2 and 8 dh del squared C bar by del X squared, because the depth average concentration is not a function of y, and we have this integral 1 minus y squared over h squared times 2 y squared y raised to power 4 h squared minus 7 over 15 h squared dy. Okay, so we can further simplify and this integral, so 3u squared over 16 dh. So we can expand the integrand, so we have 2y squared minus y4 over h squared minus 7 over 15 h squared minus 2 times y4 over h squared plus these two terms, so y raised to power 6 over h raised to power 4 and plus 7 over 15 y squared dy. Okay, so if we do this integral, we would get, so 3 u squared over 16 dh del squared c bar by del x squared. So all these terms would have a dimension of h, after the integral would have dimension of h cube. So we'll take h cube common. So the first term would be 2 over 3, then we would have 1 over 5 because we are integrating y raised to power 4, then we have 7 over 15 minus 2 over 5 plus 1 over 7 because we are integrating y raised to power 6 plus 7 over, so we have 7 over 15 and we are integrating from 0 to h y squared, so we would get h cube over 3 times 7 over 15, which is 7 over 45. So if we actually do this calculation, and that you can check yourself, so you would end up getting minus 2 over 105 u squared h squared over d del squared c bar by del x squared. Okay, so this is actually this term over here, which we actually wanted to express this equation in terms of the gradient in the mean concentration. So therefore we can now plug in this value over here and write the final equation that we desired as this. Because u bar is capital U and instead of d, so this term has the second gradient in terms of the concentration, the mean concentration, so we would get 1 plus 2 over 105 u squared h squared over d squared times the second derivative of the concentration with respect to x. So this is the parameter beta that we were talking in the previous lecture. So for flow between two parallel plates, this value of beta is 2 over 105 as we have derived over here. Now similar analysis if you do for a circular capillary, you would get beta would be 1 over 48 for a circular capillary or a channel. Similarly, instead of this parabolic flow, let's say you had a quaid flow, then you would get a different value of beta. But in all cases, you would get the effective diffusivity of the solute along the direction of the flow to be of the form d times 1 plus this constant beta, which depends upon the velocity profile, times the square of the Peckley number, and the Peckley number is defined as UH over D. That means if you have higher Peckley number, then you would have more dispersion. So now we can go back and look at the map over here, where we originally looked at log of L by H, which is the length over which the gradient in concentration takes place along the axial direction over the half height of the channel over the logarithm of the Peckley number. So we've seen till now that for large Peckley numbers we have pure convection. That is, for Peckley numbers which are greater than L over H, we will have pure convection, or you can say advection. And for extremely low Peckley numbers, we have pure axial diffusion. And we said that in between these regimes we would have both convection and diffusion that would be important. Now based on this relation, we can actually see when is axial diffusion important and when is the dispersion that is important. So first let's keep in mind that this relation is derived for the case when H squared over D, that is the radial diffusion time, is smaller than the convective time scale. So that means this is true when Peckley number is significantly smaller than L over H. So we are somewhere over here on this side of this line. Okay, and because we need significantly smaller than L over H, we are towards the right hand side of this parallel line to ensure that we are an order of magnitude smaller than this value of L over H, and that's because we are looking at a log-log plot of the Peckley number. Now looking at this relation, we see that if Peckley number is significantly larger than 1 over the square root of beta, okay, and recall that beta was 2 over 105 for 2 parallel plates and 1 over 48 for a circular channel with radius h, then you see that from this relation, which is simply based on this assumption that Peckley number is much less than L over H, then you see that the second term is actually dominating. That means this second term comes from the dispersion only, that is the combined effect of convection as well as radial diffusion, not axial diffusion. So that is, this term is actually the result of this distortion of this band, first by convection and then very fast diffusion in the radial direction. So in this regime we have that radial diffusion dominates the axial diffusion. Okay, so that is actually this regime over here. So Peckley number is large, and this is actually the Taylor dispersion regime. So we have only Taylor dispersion in this particular regime, and recall that earlier we had said that the Taylor dispersion takes place when Peckley number is significantly larger than 1, but our detailed analysis, based on our detailed analysis, we have been able to refine this limit as actually 1 over square root of beta, which certainly obeys this relation, because beta is, let's say, 1 over 48. So our revised regime starts over Peckley number which is significantly greater than square root of 48 for a circular capillary. So this is the Taylor only dispersion regime. Now we look at the completely opposite case when Peckley number is significantly smaller than square root of 1 over square root of beta. In this case, we see that in the equation for effective diffusivity, which is given by d times 1 plus beta times Peckley number squared, only the first term dominates when Peckley number is significantly smaller than 1 over square root of beta. Okay, and that means within this regime, somewhere over here, we have only axial diffusion plus convection, because if you take even smaller Peckley number, then you would have only pure axial diffusion. So actually we can draw a parallel line over here to ensure that for axial diffusion plus convection, we have Peckley number which is larger than h over L, because if this is not satisfied, then we'll just have pure axial diffusion, and we have Peckley number which is much smaller than 1 over under root beta. So this regime is actually the only axial diffusion plus convection. So this is actually that regime, and in between these two regimes we have both the axial diffusion as well as the Taylor dispersion term, which contribute to the effective diffusivity. So this is actually the Taylor-Aris dispersion regime, where we have both axial diffusion as well as the Taylor dispersion. That is important. Okay, so one really interesting thing to note is that the Taylor dispersion term is actually given by u squared h squared over d times this factor beta. Now this gives a counterintuitive result. So this is the Taylor dispersion term. Now what this term says is that certainly if you have larger h and larger mean velocity, you would have more dispersion. But interestingly, this term says that if your diffusivity is less than, sorry, this is u squared u squared h squared over d. So this term, this says that if your diffusivity is higher, so if d is large, then your Taylor dispersion is low. Okay, that's something surprising, because we would expect that if diffusivity is high, we would get more broadening of the zone of the solute band, which is convecting or advecting. But this is something counterintuitive. But this can be explained, because recall that this Taylor dispersion term is not due to axial diffusion, it is due to radial diffusion. So recall that how this term comes into picture is that we initially had this band which was deformed by convection, and then due to radial diffusion eventually we got a uniform concentration along the vertical direction. Now and it has nothing to do with the axial diffusion. Now we see that if the diffusion is high, then even for small distortion of this band, you will have quick diffusion in the radial direction. So you would attain this uniform concentration, band with uniform concentration in the vertical direction. So that means you will not have to wait for longer time for these gradients in the vertical direction to diffuse out. Okay, so that means because you are getting faster diffusion for large diffusivity in the radial direction, this band thickness will actually be smaller. So that's why you have this diffusivity in the denominator term. So higher diffusivity would actually mean you have smaller Taylor dispersion. Okay, because if you have lower diffusion constant, that means for a lower diffusivity species, the species band would first deform over a large length, and then you will have this radial diffusion. So eventually you would get a much broader band due to Taylor dispersion. So this is something which is counterintuitive. So we can now summarize what we have understood about advection and diffusion problem in a steady state flow, and advection and diffusion of a passive scalar. For certainly high Peclet numbers, we would have pure convection or advection. For very low Peclet numbers, we would have only axial diffusion. In between, we have Taylor-Aris dispersion, such that for relatively larger Peclet numbers, between 1 over under root beta and L over H, you would have Taylor only dispersion due to this kind of a distortion and radial diffusion phenomena. And for the Peclet numbers which are less than 1, much less than 1 over under root beta, but are larger than H over L, that is over in this regime we have axial diffusion plus convection, and in between these two regimes we have this Taylor-Aris dispersion where you have both axial diffusion plus this Taylor dispersion.